So we're beginning a new chapter, chapter 2, which continues number theory, but it's not the more foundational number theory stuff. It has to do with congruence mod n. Now, probably you've taken a course like discrete math or transitions to advanced mathematics, in which case you've looked at congruence mod n. And so this might be a review for you. But probably what you haven't done, you probably haven't gone in so much detail in proving things about congruence mod n. And that's what we're going to do here, since this course is a very heavy proof course. We're going to prove the details about congruence mod n. So our first definition is has to do with congruence mod n. What does A congruent to B mod n mean? So let's say you have integers a, b, and n. So you have three integers a, b, and n. And n is a positive integer, so n is greater than or equal to 1. We say that a is congruent to b modulo n, and the way we write that, we write a triple bars b mod n. That means a is congruent to b mod n, provided n divides the difference a from b, a minus b. So n divides a minus b. So that's our initial definition, and this definition is going to show up over and over and over again. So as soon as we see this, a is congruent to b mod n, we should be thinking, okay, n divides a minus b, and that's going to be key. That definition is going to be key to proving a lot of our statements regarding congruence mod n. So let's start with our first big theorem in this section. Now the theorem is 2.1, right? We're chapter 2, and we have our first big theorem. This book doesn't give it a name, but I'm going to give it a name. I'm going to call it that congruence mod n is an equivalence relation. An equivalence relation. So if you had Math 299 at Tennessee Wesleyan, and when you're doing proofs, you learn about relations, and you learn about a type of relation called an equivalence relation. An equivalence relation is a special type of relation that behaves kind of like an equal sign in some ways, in that it has these three properties called the reflexive, the symmetric, and the transitive properties. So it turns out that this relation that we're dealing with, the congruence mod n relation that we've defined here, behaves like an equal sign. It has these three properties, reflexive, symmetric, and transitive. So let's start off with some background information. Let n be a positive integer. So I'll say let n be an element of z plus. For all integers a, b, and c, these are just integers, they don't have to be positive, we have three properties. Number one, a is congruent to a mod n. This is saying a relates to itself. Number two, if a is congruent to b mod n, then b is congruent to a mod n. Or you might say, if a relates to b, then b relates to a. And three, if a is congruent to b mod n, and b is congruent to c mod n, then a is congruent to c mod n. And you could articulate this one as, if a relates to b and b relates to c, then a relates to c. So the first one, sometimes you hear the first one called the reflexive property. Every element relates to itself. A relates to A. The second one, sometimes called the symmetric property. If A relates to B, then B relates to A. And it's basically saying the order doesn't matter. You A, B, and B, A, the relation is the same between those elements. Now, the third one is sometimes called the transitive property of this relation. So any relation that has a reflexive, a symmetric, and a transitive property is said to be an equivalence relation. That's just some trivia from more foundational proof class. So we want to prove these three properties for our equivalence relation, for our congruence mod relation. Okay, let's begin our proof. See ya. Let n be a positive integer, and let a, b, and c be integers. Okay, I'm going to start with 1. Well, let's do 1 in green, okay? So I want to show that a is equivalent to a mod n. A is congruent to a. So here I'm going to do my scratch work on the side. I want to get to, so here on the side I'm doing scratch work. My proof is going to be on the left, but my scratch work, I want to show I get a is congruent to a mod n. How can I get to that? Well, let's use the definition. Remember what the definition says. A relates to b mod n precisely when n divides a minus b. So I'm going to say this is the same thing as n divides a minus a. Right? That's unwinding the definition. Now, what's a minus a? A minus a is 0, so I get n divides 0. Is that true? Does n divide 0? Yeah, right? We can write this as 0 equals n times something. N times, in fact, 0. So because this one is true right here, we can work down to a is congruent to a minus n. So let's do our proof now. Number 1, let's say note 0 equals n times 0. Okay, so that means so n divides 0, that's equivalent to, if and only if, n divides a minus a, and we know by definition that's the same thing as saying a is congruent to a mod n. And that's what we wanted to prove, right? A is congruent to a mod n for any a. That's our first one. I'll check it off. Let's go to the second one. We want to show for the second one if a is congruent to b mod n, then b is congruent to a mod n. So if I want to prove an if-then statement, I'm going to assume the antecedent here that I underlined in red, and we want to get to this part here called the consequence in yellow. So let's do a number 2. Okay, I'll do it in red. So we're going to suppose a is congruent to b mod n. Okay, and what do we want to arrive at? We want to arrive at the yellow, so I'm going to do my scratch here on the side. Now, your final draft of your proof, you don't want to show the scratch. I'm just showing the thought process. So you want to arrive at this yellow. B is congruent to a mod n. That's where I want to end up. So how am I going to get from this red to this yellow? Well, let's go forward with the red a bit. So let's say note, what does it mean if a is congruent to b mod n? Remember the definition. Let's go back. A is congruent to b mod n means n divides a minus b. So we got n divides a minus b. So that means a minus b equals n times something. Let's say nm for some integer m. Now, on my scratch, I have b is congruent to a mod n, right? What does that mean? That means n divides b minus a. That means b minus a equals n times something. We don't know what that something is right now. It should be n, not an m, n. The question is, what is this thing going to be? In other words, how can I get from my step here that I'm underlining in red to this step here that I'm circling in black? Well, we could multiply both sides of the equation by -1. So the red equation, multiply it by -1. So let's say note, if I multiply the left side of a minus b by -1, I get minus a plus b equals negative nm, right? And then we can change the order. We can write this. This is equivalent to b minus a equals n, and then we can say negative m. And that's exactly what this this circled black bit is right here. We have b minus a is n times something. That's equivalent to saying n divides b minus a, just following our scratch work. And that's equivalent to saying b is congruent to a mod n. So that's it. We've shown that if a is congruent to b mod n in red, then b is congruent to a mod n in yellow. That's the symmetric property proven. So we have one more property to prove. That's property 3. Property 3 is called the transitive property. So here we're going to assume this green stuff. If a is congruent to b mod n and b is congruent to c mod n, then we want to arrive at what's in purple here. A is congruent to C mod n. So let's assume the green, A is congruent to B mod n, B is congruent to C mod n. So here we're going to assume that. Let's suppose A is congruent to B mod n, and B is congruent to C mod n. Okay, let's unwind those definitions. So the first one tells us that n divides A minus B. And the second one tells us that n divides B minus C. Unwinding those definitions of divisibility, we have A minus B as, say, nm1, and the second one, B minus C, is nm2 for some integers m1 and m2. Now, the question is, what do we want to get to? So I'm going to do my scratch on the side. Ultimately, in purple, I want to get to A is congruent to C mod n. So I'm going to write that down here. A is congruent to C mod n. That's where I want to get. What does that mean? That means n divides A minus C. In other words, A minus C equals n times something. We'll figure out what that something is here. So my question is, how can I go from these two green equations that I'm underlining to something like this purplish equation or pinkish equation that I'm circling? Well, if you think about it carefully, you can add the two equations. So let's note, if I add the two equations, A minus B on the left side plus B minus C, that's the left sides. I'm adding the left sides. On the right sides, I'm going to get MM1 plus NM2. And the b's will cancel, right? You have a minus b and a plus b, so we'll just have A minus C equals. On the right side, you have n's in common, so we can factor out an n and get n times, in parentheses, m1 plus m2. And that's what we wanted, right? We wanted A minus C is n times something. That tells us n divides A minus C, and that tells us that's equivalent to saying A is congruent to C mod n. And that's it, right? That's what we wanted. That's what we wanted. If A is congruent to B mod n, B is congruent to C mod n, then A is congruent to C mod n. And that should be like a pinkish color or a purplish color. That's where I wanted to go, right? I wanted to go with a purple color. So that's it. That's our proof. So we got all three parts. Now in your final proof, you don't want to use the scratch work, so let me just be a good boy and erase my scratch work. Now, the whole point of me doing the scratch work on the side is to show you the thought process that I'm going through when I'm doing this. And you want to kind of do the same thing. You don't want to show your scratch work. I mean, if you want to put it on the side somewhere, you can, but don't include it in your proof. Scratch work does not go into proof. It's just kind of the thought process and the brainstorming that you go through when you're doing these. Okay, so that was Theorem 2.1. I think we can probably do Theorem 2.2 now as well. And we'll do Theorem 2.2, and then we'll go to another video. So they don't give a name in the book, but I'm going to give it a name. It's going to say Congruence modulo n preserves addition and multiplication. So we saw that the congruence mod n triple bars kind of acts like an equal sign. And in this theorem, we're going to show it even acts more like an equal sign with the plus and the multiplication operation. So let's say if A is congruent to B mod n, and C is congruent to D mod n, then there are two conclusions we can come to from this assumption. Number one, A plus C is congruent to B plus D mod n. And number two, A times C is congruent to B times D mod n. That's something that certainly works in algebra with an equal sign, right? If I have A congruent to B and C congruent to D, you can multiply the left-hand side, AC, and the right-hand side, BD, and get AC equals BD. Or you can add the right sides, a plus c on the left and b plus d on the right, and you get a plus c is b plus d. That's when you have equals, right? When you have an equal sign. Now remember, this is not an equal sign. This is not an equal sign. Don't confuse this for an equal sign, this congruence mod relation. This is something completely different. So we're going to basically show that, yeah, it acts like an equal sign here, the congruence mod and relation with respect to addition and multiplication. So addition preserves, multiplication preserves this relation. So let's go ahead and prove this. If I want to prove this if-then statement, I'm going to assume this part right after the F here, the red. So let's suppose A is congruent to B mod n, and also C is congruent to D mod n. Now probably we want to unwind those definitions for congruence mod n. That means what? N divides A minus B, and N divides C minus D. Now let's unwind those definitions of divisibility. That means what? A minus B is n times something. Let's call it m1, and C minus D is n times something. Call it m2. These are for some integers, m1 and m2. Now on the side, I'm going to do some scratch work. So number 1, I want to arrive at number 1. So thinking backwards here, I'm going to go down to the bottom of this. I'm going to write A plus C should be congruent to B plus D mod n. That's where I want to go. So what does that mean? If you unwind the definition of congruence mod n, it means n divides A plus C minus B plus D. In other words, A plus C minus B plus D equals n times something. Now we don't know what that something is right here. I'm going to put it in black. So what are we going to do here to our two equations, right? We have an equation here, an equation here. I'm underlining them in black. What can we do with those two equations to get A plus C minus B plus D as n times something? Well, you think carefully, you can add the equations again. I'm going to say we have, let's add the equations. On the left side, A minus B plus C minus D. Those are the left sides. In the right side, we have nm1 plus nm2. Okay. Now I can rearrange terms here. The A and the C we can put together. That's going to give us A plus C. And then we have minus, and then B plus D. We can put those in the parentheses, right? Because both of these B and D terms, minus B and minus D, are negative. We can put a minus and a B plus D. Then on the right side, we can factor out an n, and we can put m1 plus m2 in parentheses afterwards. So this tells me that n divides A plus C minus B plus D. And that tells me that A plus C is congruent to B plus D mod n. And that's what we wanted. That's number 1 in green. A plus C is congruent to B plus D mod n. All right, how about number 2? How can we get number 2 out of this? So that was 1 right there. Let's put that in green. Let's get a number 2 out of this. So the idea is somehow we want to do AC is congruent to BD mod n. This one's a little tricky. So what I'm going to do, I'm going to actually take my equation. So I got 2 equations, this one in the box here and this one in the box here. I'm going to multiply my first equation by C. So let's say note, or we have A C minus B C. So I multiplied the left side of that first equation in the box by C. It means we have to do it to the right side, so we're going to have nm1 C. Okay, then we're going to go to the second equation in the box, which is C minus D equals nm2. We're going to multiply that one by B. So I'm going to take B, C minus B, D and we're going to multiply the right-hand side by b. So we'll have nm2b. Now, I got these two equations. I'm going to add them together. So adding these two equations that we have right here, this one and this one, gives what? Well, I'll have, let's see, AC minus BC on the left, plus, also on the left, BC minus BD equals, then we're going to add the right sides, NM1C plus NM2B. So on the left side, the BC's can cancel, positive BC and negative BC. We get AC minus BD equals, and notice on the right side we have n's in common here. So we're going to factor out an n. We're going to have parentheses M1C plus M2B. So what does that tell you? That tells you that n divides AC minus BD. And what does that tell you? That tells you AC is congruent to BD modulo n. Is that what we wanted for the blue here? Yeah, right, we got AC is congruent to BD mod n. That's what we want. Let me write that in blue. AC is congruent to BD mod n. All right, so there we are. Theorem 2.2. All right, so we'll stop and